Hello, I'm Shashin HPM. My ID number is ID 210999618. In this video, I will walk you through the vulnerabilities identified and fixed in an e-commerce web application project, along with the implementation of OAuth for secure user authentication. For this assignment, we used the e-commerce web application developed during the third year distributed systems module. This project was selected due to its complexity, managing sensitive user data and critical e-commerce functionalities. First of all, let me explain the OAuth 2.0 implementation, which was crucial for enhancing the security of our user authentication process. We integrated Google OAuth 2.0 to allow users to log in using their Google accounts, offering both security and convenience. When a user clicks the Sign in with Google button, the front-end sends a request to the backend to generate a Google Auth authorization URL. This URL is constructed using the Google Auth 2.0 client with the necessary scopes for accessing the user's profile information. The user is then redirected to Google's sign-in page where they grant permission to the application to access their basic profile data. Once the user consents, Google redirects them back to our application with an authorization code. On the backend, this authorization code is exchanged for an access token by making a secure request to Google's token endpoint. The access token allows us to retrieve the user's profile data. Finally, the application processes this data, either creating a new user account or logging the user if they already have an account. Now we can go through with the demonstration of the integrated Google OAuth 2.0 into the application. That's all for Google OAuth 2.0 secure user authentication. Now let's move on to the vulnerabilities. I have identified and fixed 4 vulnerabilities. The first vulnerability I have identified was broken access control. Broken access control occurs when users can gain unauthorized access to resources or perform actions outside of their intended privileges. This code demonstrates broken access control due to the absence of proper role validation. As a result, unauthorized users can potentially gain access sensitive admin data because the code does not correctly enforce role-based restrictions. To fix that, I have implemented role-based access control. For that, I have created an OAuth middleware to check if the user is an admin before allowing access to the admin routes. If the user is not an admin, they receive an access denied, not authorized message, effectively preventing unauthorized access. Next, we have cross-site request forgery. This vulnerability is particularly critical in applications that handle sensitive operations or personal data, as unauthorized actions could have profound consequences for both users and the application itself. To prevent the application from CSRF, initially the implementation of cookie parser enabled the parsing of cookies, which is essential for storing the CSRF token. Then I added CSRF protection using middleware that generates a CSRF token for every post, put, and delete request. This token is then validated on the server side, ensuring that only legitimate requests are executed. An error handler was also introduced to provide a clear message and block requests if CSRF token validation failed. The frontend fetches this token and includes it in the request headers to validate the request's authenticity. Another critical issue of hard-coded secret was identified. Hard-coded secrets are sensitive credentials such as API keys or passwords hard-coded directly within the source code. This practice poses a significant security risk as it exposes sensitive information to unauthorized users and makes it difficult to manage and rotate secrets securely. To fix that, I used environmental variables by storing sensitive information in .tnv file, securely managing secrets outside the source code, and reducing the risk of accidental exposure. Lastly, the issue was absence of password hashing. Password hashing is a critical security practice used to protect user passwords from unauthorized access. Proper password hashing ensures that passwords are not stored in plain text, reducing the risk of exposure in case of data breach. To prevent that, I implemented Bcrypt to hash the passwords before storing them. This ensures that even if the database is breached, the passwords remain secure as hash passwords are significantly harder to decrypt. That's all for my part. I hope this explanation has helpful for you. Thank you.
I am Ashna Rasangika Devmani. My ID number is IT 210168220. Expose error messages vulnerability. This vulnerability occurs when an application reveals too much information in error messages, like database queries or system paths. These details can give attackers insight into how system operates, which may help the find weakness to exploit. In before fixing, initially the code expose detailed error message, such as internal server errors to users. This could unintentionally reveal sensitive details about the system, making it easier for attackers to identify and exploit vulnerabilities. Then, after fixing in this code, detailed error messages were replaced with generic ones like failed to add review item. This limits the information shown to users, reducing the risk of exposing sensitive details and strengthening the system's overall security. Insecure deserialization. This happens when an application deserializes untrusted data without proper validation. This can allow attackers to inject malicious objects or execute harmful code, leading to system compromise. And before fixing, the code deserialized data from requested body without validating it in key methods. And this opened the application to attackers, as attackers could inject malicious object into the system. In after fixing, the revised code uses express validator to validate and sanitize data before deserializing. It checks that fields like user ID and product ID are correctly formatted and uses method like trim and escape to ensure clean, safe data is processed. This prevents malicious object from entering the system. And the other vulnerability is information explosion. This vulnerability occurs when a system unintentionally reveals sensitive details such as server information or API keys, which can help attackers identify weakness and plan targeted attacks. And before fixing, the application exposed the X powered by header, which showed that the server was running on Express. This made it easier for attackers to exploit vulnerabilities specific to Express. In here, after fixing, the app disabled X powered by command. This command was added to remove the header, preventing attackers from knowing which framework is in use. The simple fix reduces the risk of exposing sensitive information and strengthens an application's security.
My name is Kavin Uttara and my ID is 2110890. Today I will be explaining the original issues and applied solution for three common security vulnerabilities: no SQL injection, content security policy, denial of service due to unprotected API endpoints. First, let's look at NoSQL injection. This occurs when user input is passed directly into database queries without proper validation or sanitization. In the original code, user input for a token was being used used in MongoDB query without any checks, allowing attackers to inject malicious data. To solve this, uh, I added input validation and sanitization using libraries like Express Validator to ensure only safe data is passed into the query. Next is content security policy, which help prevent attacks like cross-site scripting. In the original code, no CSP was implemented, which meant the browser could load resources from any external source, potentially allowing malicious script to run. To fix this, I use the helmet middleware to set strict CSP that only allows trusted resources, significantly improving security. Finally, for denial of service, the endpoint API endpoint were unprotected, allowing attackers to flood the server with requests. This could overwhelm the server and cause performance issues. I applied rate limit using the Express rate limit middleware, which restrict the number of requests each IP can make within a certain time frame, protecting the server from excessive traffic. These solutions were improved the security of the application, protecting it from common attack vectors and ensuring better performance and stability. Thank you.
My name is Gihan Sadishka and my IT number is IT 21102196. In this video, I will be discussing the important security improvements I made to the code by addressing three key areas: input validation, rate limiting, and error handling. I'll explain the original issues and the changes I applied to fix these vulnerabilities. First one is no input validation, cross-site scripting. In the original code for the sign-up route, input validation was not properly handled, especially for sanitizing user inputs like email, username, and password. This made the application vulnerable to cross-site scripting, where attackers could inject malicious scripts into the application. In the fixing code, I introduced input sanitization using validate escape function. This prevents attackers from injecting malicious scripts by escaping special characters in fields like email, username, and password. Now, before saving these inputs to the database, the code ensures that they are safe by sanitizing them and then validating them using the existing validation schema. This step adds an extra layer of security and consistency to the application. Second vulnerability is no rate limiting. Originally, the application had no rate limiting, which exposed it to serious risks like denial of service attacks. Without limiting the number of requests, an attacker could easily overload the server by sending a large number of requests in a short time, potentially causing the server to crash. After fixing, I added rate limiting using the Express Rate Limiter package. This helps restrict the number of requests that each IP address can make within 15-minute window, limiting each IP address to each IP to 100 requests. This change helps prevent abuse, keeps servers stable, and protects the application from resource exhaustion. The last vulnerability is no error handling middleware. In the original code, there was no explicit error handling middleware. This means that if an error or an exception occurred, the application could crash or show raw error messages, which would disrupt user experience and potentially expose sensitive application details to attackers. In the fixing code, I introduced error handling middleware to ensure that any errors that logged and that users receive a friendly response. Now, if an error occurs, the middleware logs the stack trace and sends a 500 internal server error message with a user-friendly notification saying something broke. This prevents the app from crashing and makes the debugging much easier. And that's all from my part. Thank you very much.